Okay, so we have an exam next week on Friday, actually, so we set aside Wednesday to review. I do have some material I want to cover on Monday with regard to, it's an introduction to control systems. Everyone in here will actually be taking controls next semester. So you have a whole semester, but just we'll touch on a few topics on Monday. But I thought what we'd do today is actually kind of start a little bit on the exam review and work through circuits problem using Laplace transform techniques. So what's the star mean? Does that mean it's really hard or recommended? I don't know.
There's a solution for that.
Oh, good, even better. So we can check the back of the book to see if we get this right. So let's work this one. So the first thing we want to do is actually set it up in the S domain. Now notice in this one too, they give us a source, it's an impulse, so it's not a realistic problem. I'll show you how to try to approximate that in LT Spice, but so it is a homework problem because non-realistic source here, but we should be able to work it using Laplace transforms. But because there is no source that's active prior to t equals 0, there are no initial conditions. There are no charge capacitors. There are no current inductors with current flowing through them. So we don't have to worry about initial conditions in this case. The first step, though, is to write the circuit in the S domain. So 200, and then here's our input called VOI, and our output in this case is actually the voltage across this capacitor. I'll call it VO. The voltage could be current, voltage across some other device, in which case the transfer function would be different. And then the capacitance, C1 is 1 millifarad, so the impedance is 1 over SC. So 1 over a milli would be 1,000 over S. And then this is 5 times larger, so the impedance would be 5 times smaller. So a couple different, techniques you could use for circuit analysis. The thing is to think about it as just a purely resistive circuit. Unfortunately, it's not quite as simple as a purely resistive circuit because it's an algebraic problem. We've got these S's floating around that we have to keep, as opposed to just pure resistances that we can combine on our calculator. So what approach do you want to take to find the output voltage? How would you solve this back in circuits 1?
Voltage division.
Say it again?
Voltage division.
Voltage division, that would work. So how would you do that?
Find the total voltage, find the total impedance, and make it a fraction with the voltage you want.
Yep. So from voltage division, it would be we want the voltage across this device, so it'd be the impedance of this device over the total series impedance. That works in a series circuit. We'll do that. You could alternatively find the total current by dividing VI by the total series impedance. Take that current, multiply it by that impedance to get that voltage. That's essentially voltage division. So voltage division would say that VO is the input voltage, the impedance of the device we're interested in over the the total impedance. All right, well, I'll just take one more step. 200 over S over 200 plus 1200 over S, combining those two. What do we want to do next? I guess we don't have to do anything. We could bring in VI right now. I prefer to clean that up a little bit just by multiplying numerator and denominator by S. We can also factor out a 200. So we got 1 over 200. Here I'll have a 1, and then I'll have an S plus 6. 2. Factor out 200 out of numerator and denominator. What is the one? S plus, does that look right? Multiply numerator and denominator by 200 over S. That's right. So, what is this, by the way? The term in parentheses. It's the transfer function, right? It would be equal to the output over the input. So by definition, it's the transfer function. What would the inverse Laplace transform of that be? So this is capital H, the little h, which we call the impulse response. Okay. So if you remember this from your Laplace transform table, this would be e to the minus 6t u of t would be the impulse response. Is it a stable system? Where's the pole here of the transfer function? At -6. Okay. Is it a stable? It is, because that's in the negative, it's in the left half plane, left half of the got a negative real part. That goes along with the impulse response being e to the minus 6t. Right? It's a decaying exponential. If this were s minus 6, that would be e to the plus 6t, which would be an increasing exponential. So in response to an impulse, we get an output that would continue to increase. But here we hit this thing with an impulse, and it decays away. Actually, this was a quite a bit simpler problem than I anticipated, I guess, but because we'll be done with this in just a few seconds. But, so a lot there about the impulse response. What's VI of S? If VI is 50 delta t, it's just 50, right? The Laplace transform of delta t is just 1. So the output voltage in the Laplace domain is 50 S plus 6. Do we need to do a partial fraction expansion on this thing? No, it's already, it won't get any simpler. There aren't multiple poles, there's only a single pole. So here pretty simply, minus 6t u of t would be the answer there. And is that the answer in the back of the book? Andrew's looking it up here. I'm just waiting. Okay. Okay, so on problems that aren't in the back of the book, though, this is fairly simple, not nearly as much algebra as involved in some of these, but it is nice to have some way to check the results. So normally we can use LT Spice. So we'll do that here. I'll show you, go through that process. So we just lay out the circuit and get a couple of capacitors. What was this? 200. And this was a millifarad. This was 5 mil. And then we need a voltage source. I'll go ahead and wire it all up. Okay. What we want to do is set up our voltage source. Okay, and we can't really have an impulse, but we can approximate an impulse with a very short pulse. Okay. Now, this thing, the impulse response actually has a time constant of a 1/6 of a second. So as long as we make our pulse kind of short compared to the time constant. So if we make it doesn't really matter, we can actually play around with the pulse width if we want, but we're probably okay if we make it a millisecond pulse, or even, that would be fine, or even 10 milliseconds. So have it start at 0, that's the initial. And then, now if we're gonna make it the on time here would be a millisecond. Now the important thing is that it have the same area. Okay. So the area of a 50 delta T is an area of 50. So if I'm going to make this thing 1 millisecond in duration, I have to give it an amplitude of 50,000, right? 50,000 times 1 millisecond would have the same. So 50K here. Delay of 0. I don't know if I need all of this. 0, 0. It's not periodic. Okay. Never really quite sure, so we just run the analysis and then I'll take a look and see if it looks right. Okay, so here we want to actually do what's called a transient analysis, and we start at 0, and then the time constant for this thing is a 1/6 of a second, so you know it decays away, and about 5 time constants are about a second. So I'll just go out to a second. Oh, that's a stop. Go out to about a second. And actually see if I get this. So there's our 50 kilovolt pulse. I'm not really interested in that. But what I really am interested in is this voltage across this capacitor, which is shown here. Okay. it looks, actually, it's going up to 55, where I got 50 there. So is that due to this approximation here? I'm guessing it is. Let me try one more thing. So what I usually like to do, and what you can do pretty easily, is actually just add to the graph here your theoretical expression. And our theoretical expression is 50 times exp of minus 6 times time. Again, every different software you work with uses different variables. In LT-SPICE, it's time to represent time. So this is our theoretical expression. Okay. Now, it looks like it lays it exactly, but there is an issue. It actually plotted our axis for a theoretical solution over there on the right, and then here's the axis for the voltage across the capacitor. Notice this is in volts, and this doesn't have units. So LT-SPICE, only if everything has the same units, will use a common axis. And so that's one of the things you have to be careful with LT-SPICE. But LT-SPICE actually understands units. To make this thing have the same units, I just need to say it's 50 volts, or multiply the whole expression by 1 volt or whatever. And then it uses a common set of axes here. I'm assuming that the difference here between, you know, our theoretical solution and what we got out of here with LT-SPICE is possibly due to the fact that my impulse response is not a true impulse. You know, I can play around with that and see if that's actually, I could make it 0.1 milli and 500K to make it even more, a better approximation. I don't think it changed much. Make it a microsecond. One micro. And then this has to be 50 meg. I think there's something else going on here. So
After we would at least have this not put our rise and fall at 0, we could just set that content choose and we make it like 1 minute a second instead.
Yeah, I think the default may be actually 10 micro or something. I think you're right. I think that is an issue. That, and you can find that in the help. It talks about that, but I know I've run into that issue before with LT-SPICE, the circuit elements, and the voltage source, and talks about I think somewhere in here, I don't want to take time to read it all. It talks about that actually if the rise and fall time are 0, it actually defaults to some 10 milliseconds instead of actually using 0. So here though, I guess if I'm going to use 1 microsecond for the duration, the rise time needs to be a proportion of that, maybe 1 pico. Okay, we'll see if it handles that. And the fall time of 1 pico. Yeah. So I don't know why LT-SPICE does that, because it does lead to problems here. If you leave the rise and fall times as 0, it actually defaults to, I want to say a millisecond or something. It's kind of a long rise and fall time. You just have to put in something that's non-zero there to get what you want. And so actually, the issue wasn't the fact that the on time. I think I can go what I have 1 millisecond before, and then make this 50K, and then run this. I guess now I'm running into the issue. Set up 1 milli. I guess now I'm running into the issue that it's not a good enough impulse. Now as I make it smaller, I guess it's, so it looks like it needs to be pretty small, 10 micro, 500 meg. The other issue is don't use M when you mean meg, because M would mean milli. Okay, what did I do? You can hear it. 500 meg times, oh, changed the wrong thing now. Should just be 5 meg for 10 micro. There we go. That's getting pretty close. It looks like, so, well, we've done enough at least that I'm fairly confident that this is the right theoretical response. Do you want to work another problem? Or see anything else in LT-Spice?
Work another problem.
Which, you have a particular problem?
Not really, no. Let's do some integration.
Say that again?
Integration.
Something with integration?
I need to work with that to calculate.
Oh, you mean like with an op-amp integrator?
Yeah.
So, okay, so most of that, what you want to use for like the integrators. Yeah, we can see if these op-amp integrators actually integrate, right? Is that what you want?
Yes.
So here's the basic circuit. Now 1/S is an integrator. Now this is an inverting integrator, but if I do this in LT-Spice, I don't have to use realistic versions of resistance and capacitance. I can use a 1 ohm resistor and a 1 farad capacitor, and LT-Spice is fine with that. Okay. And then that would mean it's an inverting integrator. Okay. So here's LT-Spice. Okay, just do a new one. Let's save it. Okay, so here we want to pull out an op-amp, and I'm going to get one out of the University of Evansville components. I'll show you why in just a second. Okay, let's see. Op-amps. There's this UE op-amp. Now, you actually have several different models here. The default is a 741, but if I click on the 741 style op-amp, but if I click on it here and choose simple, let me start here. The simple is the one that's closest to the ideal op-amp. And for the simple one, you don't even have to hook up the DC power supplies. For the 741, you do. This is kind of a theoretical model. But here, So probably the easiest thing to do is actually just make this a sine wave. Is that okay? With a 1 volt amplitude, and then I'll just give it a 10 hertz frequency. And then, so now if I'll do this out to 1 second. So here's what the input looks like, and here's what the output looks like. Now, let's see.
What
Pardon?
I was going to, that was it.
No. So this is actually the minus the integral of the sine wave. And I actually screwed up by making it 10 hertz probably. But the integral of a sine is cosine, right? But it would be 1 over 20 pi cosine of 2 pi 10t. Let me make the frequency 1 over 2 pi. Can I do that? Is that all right? So that this actually becomes 1. The issue is when you do the integration, you get that 1 over 20 pi, so the output is just a lot smaller in amplitude than the input. I mean, we should be able to figure that out. What's 1 divided by 20 pi? Do that on your calculator. Let me actually delete this trace and then just run this so we can see. Is it like 31 or something? 0.031?
0.0159.
So this is the sine. Actually do it this way. Delete this trace, add a plot pane, and plot the output. Okay. So there should be a 90-degree phase shift between the sine and the cosine. Or not, well, if you'll notice here, this starts, the output actually starts at its peak, like a cosine. Or the sine here starts at 0. So it looks like it has the right phase relationship, that the output is the input of the output's the integral of the input. Actually, it's probably a little, let me try one other type of input. If you integrate a square wave, you should get a sawtooth type waveform. So if I make this a pulse on for 1 micro, I'll get rid of those things, 1 micro, and then have it on for 1 second with a period of 2 seconds. And then now run this. I need to go a lot farther out in time though, with those long times. It's going down because of the DC offset. It's integrating a DC, so I actually need to change this. It's probably easier to do this. I change this to a differentiator to show you how it does calculus. So to get the differentiator, oops, wrong hand. I need to just swap the resistor and the capacitor. And then now if I differentiate this pulse though, I'll get a series of short, I should get a series of short spikes, because when you differentiate the edges, you get essentially these impulses. But if I can make this thing kind of like a sawtooth, I think it'll be a little more instructive. I can do that by making it, giving it like a ½ second rise time and a ½ second fall time with no on time. Is that right? No. What's that? 1 volt peak. No on time in a period of 1 second. Let's see what that looks like. I'm not sure that's happening. It's actually so we put them both on the same. The scale's different. But remember it's inverting. But now the blue should be the derivative of the green. So the negative derivative. You notice here that the slope is positive, has constant derivative. So the derivative there is, in this case, it's negative because it's an inverting op amp. Okay. Here where the slope is negative, the output's positive. Slope's positive, the output's negative. Theoretically here, what is the slope here? I have it going 1 volt in ½ a second. So 1 divided by a half would be 2, right? But because of the minus, it's a -2. And then here, so it'll do calculus for you. Actually, let's see. Again, I said this is kind of the ideal op amp and what we would expect here. Let me change this a little bit so that it actually does 1 second and then give it a period of 2. Then I think the amplitudes will be roughly the same then, won't they? Except it goes between plus and -1, and this goes from whatever. But is that okay, Rodney? The negative. Okay, so if I switch it over to the default, or actually make it the 741. One thing you'll notice right often is that actually the output's following the input, which surprises me, but it's wrong. But using the 741 model, I have to include the power supplies. So probably the easiest way to do that is just put in 2 voltage sources. Make this one go plus 20, and this one minus 20. And then if you label the nodes, by convention, the plus one is called BCC. And two nodes that are labeled the same are connected, but this way I don't have to have all the crossing wires. And then the negative one is EE. Now let's see what we get. Still not working here at all. So I don't know what's wrong with this model. That one's even worse. I have to play around with it and see why it's not working with the 741 op-amp model. Maybe that I've got one of these things. I think they're connected. Minus 20. Okay. All right, we got a few minutes. We take a look at another one of these circuit problems. This one 4.8 is it? It's got initial conditions but no source. So we looked at one that had a source but no initial conditions. So maybe let's look at 4.8 here. This you would only have the zero input response. So determine the current through the inductor given before the closing of the switch. The capacitor is charged at 24 volts. So, but we're looking at after the switch is closed. And then the way we handle the initial condition, and you can do it either of two ways, with a voltage source in series with the capacitor, or a current source in parallel with the capacitor. It doesn't really matter. Let's get the element values in here. R is 1, L is 0.8, C is 0.25, so that would be 4 over S. And we need to find this current. Let's do it with a current source in parallel, and that 24 volts across that capacitor initially. So you have to go back and look at the beginning of the chapter here, I think, with the sorry, went too far. So here are the different models. And so it's CVC. And the direction is important here too. So we had 24 volts, right? And it was a quarter of a farad. So 24 divided by 4, this should be just 6. I think that's right, wasn't it 24 volts initially, and then. Okay. So how do you want to solve this problem? You could use current division. Let's go ahead and get, we could get the total, it's called susceptance, the sum of the reciprocal impedances. Well, let's do it this way. ZT is, the total impedance is the reciprocal of the sum of the reciprocals. 1 plus S over 4 plus 1 over 0.8 S. All right, that's the total impedance. So let me multiply through by S, I guess. S over 4S. So here I'm going to get an S squared and 4S. And then I have a 4 divided by 8/10. That's 40 divided by the total impedance. I think I did that right. Multiply numerator and denominator by 4S. So here I get S squared plus 4S. And then 4 divided by 0.8 is 5. So now I can get the total voltage pretty easily. It's just my current times my impedance. So it's going to be 24S over S squared plus 4S plus 5. And then finally I can get my inductive current. It's going to be my voltage divided by 0.8S. So my S's cancel. 24 divided by 0.8, what is that? S squared plus 4S plus 30. Okay, so here's my current in the Laplace domain. I'm going to do a partial fraction expansion now, because this does have two roots. Are they real or complex? Fortunately, they're complex, I think, right? So actually, we don't have to do this S plus 2 squared. So this would be S squared plus 4S plus 4 plus 1. Okay. And they're equal. And then I think this will be in our Laplace transform table. So this is 13. I put it in this form, 1 over S plus 2 squared plus 1 squared. So that means the inductive current is 30 e to the minus 2t sine of t, ut. Is that okay? Any questions about that? I'm never confident enough, and there's just too many opportunities for error. So those values. Wire this thing up. What was the resistor? Was it 1?
Yes.
And then the capacitor was 0.25.
Yes.
The inductor was 0.8, right?
Yes.
0.8. And then the other thing with the capacitor, it had an initial voltage of 24.
Yes.
So now if we run this, so according to that, it's got a, you know, it's a decaying sinusoid, okay, and the time constant's about half a second, okay, 1/2. So if I run it out to about 3 seconds, it should be essentially have decayed away. So we can do this and the stop time of about 3 seconds. Here, you have to check this skip initial operating point solution. That throws in this UIC, which is, it's funny the way it's worded, but that means actually use the initial conditions. And so this is what I get out for the LT spice inductor current. Okay. Now, a couple things, if you want to compare that to the theoretical, just hit Control A, and what was it? It was 30 amps times EXP of -2 times time. Now, I'm going to put in this sine of time, and it's wrong. But part of the reason, I don't know if this is the only thing that's wrong with it, but part of the reason is in LT Spice, unlike almost every other software package in the world, the argument to the sign here has to be in degrees, whereas here it's in radians. So I have to convert this actually to degrees to make LT Spice happy. So I have to multiply by 180 and divide by pi. And then there they overlap. So I'm pretty confident that we actually got the right solution there. Spend as much time actually getting LT Spice to plot the right thing as you can actually solving the problem sometimes. But it's nice when they agree, because then you can be fairly confident that you've got the right result. Okay, have a good weekend.